Hello and welcome to Space Historians. I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind, to step away from screens and deadlines and the relentless rush of now, and step quietly into a question that has puzzled astronomers for decades. A question about edges, about boundaries, about whether the solar system truly ends or simply fades into something larger. Tonight, we're travelling to the Oort cloud, an invisible sphere of frozen fragments that may stretch nearly a light year from the Sun. No telescope has ever photographed it. No spacecraft has ever reached it. And yet most astronomers believe it exists, a vast halo surrounding everything we know, holding trillions of icy bodies in silent orbit. Some call it the edge of the solar system. Others wonder if it's not an edge at all but a threshold, a place where our star's influence dissolves into the galaxy's embrace, where the familiar gives way to the unknown. Here in this space between certainty and mystery, we wander together through discoveries that challenge what we thought we understood. We follow the paths of comets that arrive from unimaginable distances, blazing through our skies before retreating into darkness. We stand at the heliopause, where Voyager crossed into interstellar space, yet still the Oort cloud lies beyond, patient and unseen. We imagine what it means for there to be an edge at all, when reality seems to resist every boundary we try to draw. If you enjoy these quiet journeys beyond our world, a like and subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen, breathe, and let yourself drift toward the edge of reality itself. To understand the Oort cloud, we must first return to the beginning, to a time before planets, before moons, before the Sun itself had ignited. 4.5 billion years ago, this region of space held nothing but a vast cloud of gas and dust, cold and diffuse, drifting in the darkness between stars. Within that cloud, gravity was already at work, pulling material together grain by grain, atom by atom, concentrating mass in ways that would eventually give birth to everything we know. At the center of this collapsing cloud, pressure and temperature climbed until nuclear fusion sparked. The Sun was born, blazing into life, flooding the surrounding space with light and heat and a fierce wind of charged particles. Around it, the remaining gas and dust settled into a spinning disk, a protoplanetary disk where worlds would form. Within that disk, particles collided and stuck together, building larger and larger objects through a process both violent and patient. Close to the Sun, where temperatures were high, rocky planets formed. Mercury, Venus, Earth, Mars, worlds of metal and stone that could withstand the heat. Farther out, beyond what we now call the frost line, temperatures dropped low enough for water to freeze, for methane and ammonia to condense into ice. Here the gas giants assembled, Jupiter and Saturn, Uranus and Neptune, gathering not only rock and ice but enormous envelopes of hydrogen and helium. These giants grew massive, their gravity reshaping the entire disk. But not all material joined the orderly construction of planets. Some fragments were flung outward by gravitational encounters, tossed like stones from a sling. When a small, icy body passed too close to Jupiter or Saturn, the giant's gravity could accelerate it, sending it on a trajectory that carried it far beyond the realm of planets. Some of these ejected fragments escaped the solar system entirely, lost to interstellar space. Others remained loosely bound to the Sun, settling into vast, elongated orbits that took them thousands, even hundreds of thousands of times, farther from the Sun than Earth. Over millions of years, this process scattered countless icy bodies into the outermost reaches of the Sun's gravitational influence. They formed a spherical cloud, not concentrated in a disk like the planets, but distributed in all directions, surrounding the entire solar system. This was the birth of the Oort cloud, though it would be billions of years before anyone gave it a name, billions of years before anyone realized it existed at all. The cloud formed from leftovers, from fragments that never became planets, from ice and rock and frozen gases that were exiled to the edge. In a sense, the Oort cloud is made of the solar system's outcasts, the material deemed surplus, the pieces thrown away. And yet these outcasts have endured, preserved in the deep cold, holding within them the chemistry of the original protoplanetary disk. While planets evolved, erupted, eroded and changed, the Oort cloud remained frozen, a time capsule at the edge of reality. The setting of our story is both ancient and ongoing. The solar system began as chaos, a swirling mass of debris circling a newborn star. From that chaos came order, the elegant arrangement of planets we know today. But beyond that order lies the Oort cloud, a reminder that not everything was tamed, not everything fell into place. At the farthest edge of the sun's domain, in a sphere so vast it defies imagination, the remnants of creation still drift, silent witnesses to the violence and beauty of beginnings. This is where our journey begins, not in the familiar orbits of Earth or Mars, but in the understanding that the solar system is far larger than we once believed. The Sun's family extends not just to Neptune or Pluto, but outward into a halo of ice that marks the transition between what belongs to us and what belongs to the galaxy. The Oort cloud was born in the chaos of formation, and it endures at the edge of reality, waiting to tell its story. For centuries, astronomers catalogued comets without truly understanding where they came from. These luminous visitors would appear suddenly in the night sky, growing tails that stretched across the heavens, moving perceptibly from night to night before fading back into invisibility. Some returned predictably, like Halley's Comet with its 76-year cycle. Others appeared once and vanished forever, their orbit suggesting they would not return for thousands of years, if ever. By the early 20th century, astronomers had amassed detailed records of cometary orbits. They noticed patterns. Short-period comets, those returning every few decades or centuries, seemed to originate from the region beyond Neptune, from what would later be called the Kuiper Belt. But long-period comets, those with orbital periods measuring in thousands or millions of years, arrived from all directions. Their paths were not confined to the plane of the planets, but came tilted at every possible angle, as if raining down from a spherical source. This randomness was puzzling. If all comets formed in the same disk that gave birth to planets, they should share the disk's orientation. They should arrive from predictable directions, aligned with the ecliptic plane. Instead, long-period comets behaved as if they originated from a vast sphere surrounding the entire solar system. But no such sphere had ever been observed. No astronomer had seen evidence of anything beyond Neptune except empty space. In 1950, a Dutch astronomer named Jan Oort published a paper that would change our understanding of the solar system's structure. Oort was already known for his work on galactic rotation, for showing how stars orbit the center of the Milky Way. Now he turned his attention to comets, studying their orbits with the same mathematical rigor he had applied to galaxies. He calculated where these long-period comets must have originated based on their trajectories, working backward through time and space. His conclusion was elegant and audacious. The long-period comets, Oort proposed, came from a vast reservoir of icy bodies surrounding the solar system at extreme distances. This reservoir formed a spherical shell, not a disk, which explained why comets arrive from every direction. The shell, he calculated, might extend from thousands of astronomical units away to perhaps 50,000 or even 100,000 astronomical units, nearly a light year from the Sun. Within this shell, trillions of icy fragments drifted in slow orbits, most of them undisturbed for billions of years. Occasionally, Oort reasoned, one of these distant bodies would be perturbed. A passing star might approach close enough to alter orbits with its gravity. The subtle tidal forces of the Milky Way itself might nudge objects over long timescales. When such a disturbance occurred, a comet would be sent falling inward, beginning a journey that could take millions of years, accelerating as it approached the Sun until it blazed through the inner solar system as a spectacular visitor. The beauty of Oort's proposal was that it explained not only where comets came from, but why they kept appearing. The reservoir was so vast, containing so many objects, that even after billions of years of sending comets inward, it would still hold enough fragments to continue supplying them for billions more. The solar system was not running out of comets because the source was almost inexhaustible. The cloud, as it came to be called, was a cosmic reserve, a halo of frozen potential surrounding everything we knew. Oort's discovery was not made with telescopes or spacecraft. It was made with mathematics, with careful observation of orbital mechanics, with the patient work of tracing paths backward to their source. He saw the fingerprints of an invisible structure and inferred its existence. The Oort cloud became one of astronomy's great invisible truths, accepted not because we can see it directly, but because the evidence for it is overwhelming. Every long-period comet that enters our skies is a messenger from that distant halo, proof that the cloud exists, even though it remains beyond our vision. The spark of mystery was this: how could something so vast, so fundamental to the solar system's structure, remain completely unseen? How could we know it was there without ever observing a single object within it? Oort's work showed that science is not always about direct observation. Sometimes it is about inference, about noticing patterns and following them to their logical conclusions. The Oort cloud exists in equations and in the trajectories of comets. It exists in the minds of astronomers who understand that what we cannot see can still be real, still be knowable, still reshape our understanding of where the solar system ends and the galaxy begins. This discovery opened a new chapter in our cosmic story. The solar system, once thought to end with the outermost planet, now extended almost unimaginably farther. The sun's influence reached across distances measured not in millions of kilometers, but in trillions. And at the edge of that influence, in a sphere so large it brushed against the space between stars, the Oort cloud waited, a hidden frontier that would challenge every assumption about boundaries, about edges, about where reality itself might end. When Jan Oort published his proposal in 1950, the astronomical community found itself facing an uncomfortable paradox. Here was a structure that, if it existed, would be the largest component of the solar system by far, dwarfing everything else in sheer volume and extent. And yet, this structure was completely invisible, known only through inference, through the mathematics of cometary orbits. For some astronomers, the elegance of Oort's solution was immediately compelling. For others, the idea of accepting something so vast yet unseen felt like a leap too far. The initial response was mixed, caught between admiration for the brilliance of Oort's reasoning and skepticism about claims that could not be directly verified. Astronomy had always been a science of observation, of pointing telescopes at objects and studying their light. The Oort cloud offered no light to study, no objects bright enough to detect, no way to confirm its existence except by watching comets fall inward and trusting the calculations that trace them back to their source. Some astronomers embraced the idea immediately. They recognized that Oort had solved a genuine puzzle, that the random arrival of long-period comets from every direction in the sky demanded an explanation, and the spherical cloud was the simplest, most elegant answer. These scientists began incorporating the Oort cloud into their models of solar system formation, treating it as a natural consequence of the gravitational scattering that occurred when the giant planets were young and mobile. Others were more cautious. They did not dispute Oort's mathematics, which were sound, but they questioned whether such a structure could remain stable over billions of years. Would not passing stars disrupt it entirely, scattering its contents into interstellar space? Would not the tidal forces of the galaxy itself pull it apart? These were reasonable concerns, born from an understanding that the Oort cloud, if it existed, occupied a precarious position at the very edge of the sun's gravitational influence. Over the following decades, further study gradually built confidence in the cloud's existence. Astronomers refined their models of how the solar system formed, showing that gravitational scattering by Jupiter and Saturn would naturally eject vast numbers of icy bodies into distant orbits. They calculated how the cloud would evolve over time, showing that while individual objects might be lost, the overall structure could remain stable for billions of years, constantly replenished from the inner regions during the solar system's youth. The discovery of more long-period comets, each with orbits consistent with an origin in a distant spherical reservoir, added weight to Oort's hypothesis. Every new comet was another data point, another piece of evidence. When astronomers studied the distribution of these cometary orbits, they found exactly the pattern Oort's cloud predicted. The arrivals were random in direction but clustered at certain distances. suggesting a shell structure with inner and outer boundaries. There was also a sense of wonder in the response, a recognition that the solar system had suddenly become far stranger and more magnificent than anyone had imagined. To think that we lived inside a vast sphere of frozen fragments, that the familiar planets and moons occupied only the tiniest central region of a structure, extending almost a light year in every direction, was humbling and exhilarating. The Oort cloud transformed the solar system from a neat arrangement of planets into something wild and mysterious, a cosmic architecture that blurred the line between what belonged to the Sun and what belonged to the galaxy. Some astronomers found beauty in the cloud's invisibility. It was a reminder that the universe contains more than what we can see, that reality extends beyond the reach of our instruments. The Oort cloud existed in the realm of theory and inference, yet it was as real as anything we could photograph. It challenged the notion that only the observable matters, suggesting instead that some of the most important structures in the cosmos might forever remain beyond direct observation. For the public, the Oort cloud entered popular imagination slowly. Unlike planets or stars, it offered nothing dramatic to photograph, no colourful images to capture attention, and yet it became a symbol of the unknown, a reminder that even our own solar system held secrets. Science fiction writers began placing stories there, imagining civilizations hiding in the cloud's vastness, alien probes drifting among its icy bodies, human explorers venturing into the ultimate frontier. The response to Oort's discovery was ultimately one of acceptance, though it took time. The cloud became part of the standard model of the solar system, taught in textbooks, incorporated into planetary science. Astronomers spoke of it with confidence, even though none had ever seen it directly. It became an invisible truth, accepted on faith in mathematics and in the evidence of comets, a structure so large that our entire conception of the solar system had to expand to accommodate it. What made the response so profound was the shift it required in thinking. The solar system was no longer a bounded entity with clear edges. It was instead a layered structure, with the planets at the centre, the Kuiper belt beyond, and then this vast diffuse halo extending into the space between stars. The Oort cloud did not mark a hard boundary, but a gradual fading of the Sun's influence. It was both part of the solar system and part of the galaxy, a transition zone where belonging became ambiguous. In the end, the first response to the Oort cloud was awe. Awe at its scale, awe at the elegance of its discovery, awe at the realization that something so vast could exist unseen for billions of years, waiting patiently for someone like Jan Oort to notice the patterns in cometary orbits and trace them back to their source. The cloud became a monument to the power of human reasoning, proof that we could know things beyond what our eyes could see, that mathematics and observation together could reveal hidden structures at the very edge of reality itself. The Oort cloud presents a fundamental contradiction that lies at the heart of modern astronomy. On one hand, it is a scientific hypothesis, grounded in mathematics, supported by decades of observation, accepted by the vast majority of planetary scientists. On the other hand, it remains completely unobserved, a structure inferred rather than seen, known only through its effects rather than through direct evidence. This tension between certainty and invisibility creates a space where science and mystery meet, where knowledge coexists with the unknown. The contradiction begins with scale. The Oort cloud is thought to contain trillions of objects, perhaps more icy bodies than there are stars in the galaxy, and yet we have never observed a single one of them in their native orbit. The comets we see are those rare individuals that have been perturbed and sent falling inward, their ices sublimating in the sunlight to create the glowing comas and tails that make them visible. But those are exceptions, perhaps one in a billion. The rest remain dark, frozen, utterly invisible against the blackness of space. This invisibility is not accidental but fundamental. At the distances where the Oort cloud exists, sunlight is so faint that even a mountain-sized block of ice would reflect almost no light. Our most powerful telescopes cannot detect such objects unless they pass very close to us, or are heated enough to outgas. The cloud exists beyond the practical limits of observation, in a realm where even if we pointed every telescope on Earth in the right direction, we would see nothing but darkness punctuated by distant stars. Science demands evidence, and yet here we accept a structure based on inference alone. The evidence comes indirectly through cometary orbits, through calculations of trajectories, through models of solar system formation that predict such a cloud should exist. But these are not photographs, not spectra, not the tangible data that usually forms the bedrock of astronomical knowledge. The Oort cloud asks us to trust mathematics, to believe that patterns in data can reveal truths about things we cannot see. Some might argue this is not truly a contradiction, that inference is a valid form of evidence, that we accept many things in science based on indirect observations. We have never seen an atom directly, yet we know they exist. We have never visited the core of the Earth, yet we understand its composition. Dark matter itself is accepted based entirely on gravitational effects, not on direct detection. In this view, the Oort cloud is simply another example of how science operates, using logic and evidence to build understanding of things beyond our immediate perception. But the Oort cloud pushes this further than most invisible structures. It is not just distant, but almost impossibly distant. Not just dim, but completely dark. Not just difficult to observe, but perhaps permanently beyond our observational reach. Even if we develop far more powerful telescopes, even if we send probes into the outer solar system, the vastness of the cloud and the faintness of its constituents may keep it forever in the realm of the inferred rather than the observed. This creates a philosophical tension. How do we know the cloud is real? What does it mean to say something exists if we can never observe it? These questions touch on deeper issues in the philosophy of science, on the nature of knowledge itself. We believe the Oort cloud exists because its existence explains observations that would otherwise be mysterious. The appearance of long-period comets from random directions, the statistics of their orbital distributions, the chemistry they carry from the early solar system, all of this makes sense if the cloud is real. Yet there remains room for doubt, not serious scientific doubt perhaps, but the kind of doubt that comes from recognizing the limits of certainty. Could there be alternative explanations for long-period comets? Could they originate from some other source we have not considered? Most astronomers would say no, that the Oort cloud is the only explanation that fits all the evidence, but the fact that we cannot directly observe it leaves a small space for uncertainty. This uncertainty is not a weakness, but a feature of how science approaches the unknown. Science is comfortable with provisional knowledge, with accepting ideas that best explain the evidence while remaining open to revision if new data emerges. The Oort cloud is accepted because it works, because it explains what we observe, because no better explanation has been proposed. But that acceptance is based on inference rather than certainty, on patterns rather than direct observation. The contradiction between science and mystery in the Oort cloud also reflects something deeper about the edges of reality. At the boundaries of what we can know, certainty always fades into probability. Observation gives way to inference, and hard facts blend into educated guesses. The Oort cloud exists at such a boundary, both literally and figuratively. It is at the edge of the solar system, at the edge of our observational capabilities, at the edge of what we can claim to know with absolute confidence. And yet this does not diminish its importance. If anything, the fact that the Oort cloud remains unseen makes it more significant, not less. It reminds us that reality extends beyond what we can observe, that the universe is larger and stranger than what our instruments can capture. It teaches us humility, showing that even in our own solar system, even in the region dominated by our own star, there are vast structures we can only imagine. The contradiction is this: we know the Oort cloud exists, yet we have never seen it. We map its structure, calculate its mass, predict its behavior, yet it remains invisible. This is not a failure of science, but a triumph, a demonstration that human reasoning can extend beyond the limits of human senses. We have built a picture of the solar system that includes things we cannot see, and that picture is richer and more accurate because of it. In the end, the contradiction between science and mystery at the Oort cloud is not something to resolve, but something to embrace. It shows us that knowledge and mystery can coexist, that what we understand and what we do not understand are not separate realms but parts of a continuum. The cloud stands at the threshold. reminding us that every answer opens new questions, that every boundary we map reveals new territory beyond. Science may never fully conquer mystery, but in places like the Oort cloud, it can illuminate the darkness enough to show us what lies just beyond our reach. While Jan Oort's basic proposal of a distant spherical reservoir of comets gained widespread acceptance, the details remained subjects of intense debate. Astronomers divided into camps, each proposing different models for the cloud's structure, its origins, its stability, and its relationship to the rest of the solar system. These divisions were not bitter conflicts, but productive disagreements, the kind of scientific debate that refines understanding and pushes knowledge forward. One major question concerned the cloud's structure. Oort had proposed a single spherical shell, but as computer models grew more sophisticated, astronomers began to suspect the reality might be more complex. Some suggested the cloud had two distinct regions, an inner Oort cloud beginning perhaps 2,000 astronomical units from the Sun, and extending to 20,000, shaped more like a thick disk than a perfect sphere, and an outer Oort cloud beginning around 20,000 astronomical units, and extending to perhaps 100,000, this one truly spherical in distribution. The inner cloud, according to these models, would be the original structure formed during the solar system's youth when icy bodies were scattered outward by gravitational encounters with the giant planets. The outer cloud would represent objects that had their orbits further modified by passing stars and galactic tides over billions of years, gradually becoming more randomly distributed. This two-part structure explained certain patterns in cometary orbits better than a simple single shell. Other astronomers questioned how the cloud maintained its population over time. Passing stars should disrupt orbits, sending some comets into interstellar space and others falling toward the inner solar system. Over 4.5 billion years, should not the cloud have been depleted or scattered entirely? Some theorists proposed that the cloud was constantly being replenished, but even now gravitational interactions in the outer solar system were sending new objects into distant orbits. Others argued that the original population was so vast that even billions of years of losses left plenty of material remaining. Theories also divided over the cloud's origins. The standard model held that Oort cloud objects formed in the same protoplanetary disk that gave birth to the planets, somewhere between the orbits of Jupiter and Neptune, before being ejected outward. But some scientists proposed that a portion of the cloud might have been captured from interstellar space, that, as the Sun moved through denser regions of the galaxy in its youth, it might have gravitationally captured passing objects and added them to the cloud. This capture hypothesis was controversial. Critics pointed out that capturing objects from interstellar space is difficult, that most would pass by without being trapped. Supporters argued that in the early solar system, when the cloud was still forming, conditions might have been more favourable for capture. If true, this would mean the Oort cloud contained not only material from our solar system's birth, but also fragments from other stellar systems, immigrants from elsewhere in the galaxy. Another division concerned the cloud's current state. Some models suggested it was relatively stable, with objects remaining in predictable orbits unless disturbed. Others proposed that the cloud was dynamic, constantly churning under the influence of galactic tides and passing stars, its structure changing significantly over millions of years. These different views led to different predictions about comet arrival rates, about how often we should expect new long-period comets to appear in the inner solar system. There were also debates about the cloud's composition. Most astronomers agreed the objects were primarily water ice mixed with frozen carbon dioxide, methane and ammonia, similar to what we observe in comets. But some theorized that the Oort cloud might contain more diversity than we imagine, including larger bodies, possibly dwarf planets or even rogue planets ejected from the inner solar system during the chaotic early period. Such large bodies would be even harder to detect, but could play important roles in perturbing smaller objects. The question of whether the Oort cloud truly defined the edge of the solar system also divided opinion. Some astronomers argued that since the cloud was still gravitationally bound to the Sun, it should be considered part of the solar system, making the system's edge far more distant than traditionally thought. Others contended that the cloud was so loosely bound, so easily influenced by external forces, that it was really a transition zone between the solar system and interstellar space, rather than a true component of either. These theoretical divisions were not mere academic exercises, but reflected genuine uncertainty about a structure that remained beyond direct observation. Each theory made different predictions about what we should observe in cometary orbits, about how the cloud should evolve over time, about what future observations might reveal. As astronomers refined their models and gathered more data on long-period comets, some theories gained support, while others fell away. What made these divisions productive was that they were grounded in evidence and mathematics, rather than speculation alone. Theorists proposed mechanisms, calculated their effects, made predictions that could be tested against observations. When new comets were discovered, their orbits provided data that helped distinguish between competing models. When computer simulations of solar system formation grew more sophisticated, they showed which scenarios were plausible and which were unlikely. The debates also reflected different philosophical approaches to the unknown. Some scientists preferred simple models, arguing that the Oort cloud should be understood using the fewest assumptions necessary to explain the data. Others embraced complexity, proposing elaborate structures and multiple formation mechanisms to account for subtle patterns in observations. Both approaches had merit. Both contributed to understanding. In time, a rough consensus emerged. The Oort cloud likely had a complex structure with inner and outer regions. It formed primarily from solar system material scattered outward during the era of planet formation, though a small fraction might have been captured from interstellar space. It was dynamic rather than static, constantly evolving under external influences. And it represented a genuine boundary of the solar system, though that boundary was not sharp but gradual, a fading of the sun's influence rather than a hard edge. Yet even with this consensus, uncertainty remained. The cloud's exact population, its precise distribution, the details of how it evolved, all of these remained open questions. The theories had divided minds not because the evidence was unclear, but because the subject was so distant, so difficult to observe, that multiple interpretations remained plausible. The Oort cloud continued to be a place where knowledge met mystery, where what we understood blended seamlessly into what we could only imagine. Understanding the Oort cloud required a different kind of investigation than most astronomical research. Since the cloud itself could not be observed directly, astronomers had to become detectives, piecing together evidence from scattered clues, building a picture of the invisible through careful analysis of the visible. The pursuit became a study of comets, of orbital mechanics, of the subtle ways distant objects revealed themselves through their trajectories and their chemistry. The primary method of investigation was tracking long-period comets. Every time a new comet was discovered, astronomers would calculate its orbit with precision, determining where it came from and where it was going. These calculations required careful observations over weeks or months, measuring the comet's position against background stars, noting how its motion changed as it fell toward the sun and then climbed back out into the darkness. From these measurements, orbital elements could be derived, numbers that describe the shape and orientation of the comet's path through space. What made this detective work challenging was that most long-period comets were observed during only a tiny fraction of their orbits. A comet might spend millions of years in the distant reaches of the Oort cloud, then a few thousand years falling inward, then just a few months in the inner solar system where we could see it, before climbing back outward for another long journey. Astronomers were trying to understand an orbit spanning light years based on observations covering perhaps a few million kilometers, like trying to describe an entire continent after seeing only a single street corner. Despite this limitation, patterns emerged. When astronomers compiled catalogues of long-period comet orbits, they found that most of these objects had aphelia, their farthest points from the Sun, clustered in a range between 10,000 and 50,000 astronomical units. This clustering was significant because it suggested a source region at those distances. If comets originated randomly from interstellar space, their aphelia would be distributed differently. The pattern pointed to the Oort cloud as a specific structure rather than a random scattering of objects. The investigation also required understanding how comets were perturbed from their distant orbits. Astronomers studied the motions of nearby stars, calculating how often and how closely other stellar systems passed near our own. They modelled the effects of galactic tides, the subtle gravitational influence of the Milky Way's spiral arms and central bulge on objects at extreme distances from the Sun. These calculations showed that perturbations were frequent enough on astronomical timescales to explain the steady stream of new comets entering the inner solar system. Computer simulations became essential tools in the pursuit. Researchers created digital models of the early solar system, populating them with millions of test particles representing icy bodies. They then ran the simulations forward in time, watching as gravitational interactions with Jupiter and Saturn scattered these particles into distant orbits. The simulations showed that forming an Oort cloud was not just possible, but inevitable, a natural consequence of how giant planets rearranged material during the solar system's youth. These simulations also allowed astronomers to test different scenarios. What if Jupiter had formed at a different distance? What if there had been a fifth giant planet that was later ejected? What if the Sun had passed through a dense star cluster in its early history? Each scenario produced a different final distribution of Oort cloud objects, and by comparing these predictions to the observed patterns in cometary orbits, researchers could constrain which scenarios were most likely. The investigation extended to the chemistry of comets as well. When comets approached the Sun and began outgassing, astronomers could study the composition of the released material using spectroscopy. They found water vapor, carbon monoxide, carbon dioxide, methane, ammonia, and more complex organic molecules. The ratios of these compounds provided clues about where and when the comets formed. Comparing comet chemistry to models of the early solar system's temperature and composition helped confirm that these objects originated in the outer regions of the protoplanetary disk. Space missions added crucial data to the investigation. The Giotto spacecraft flew past Halley's Comet in 1986, returning close-up images and measurements. Though Halley was a short-period comet from the Kuiper belt rather than the Oort cloud, it provided insights into what cometary nuclei looked like, how they outgassed, what they were made of. Later, the Rosetta mission spent 2 years studying Comet 67P Churyumov-Gerasimenko, revealing intricate details of cometary structure and composition that informed understanding of all comets, including those from more distant reservoirs. The pursuit of knowledge about the Oort cloud also involved studying other stellar systems. As astronomers discovered planets around other stars, they found evidence that those systems might have their own Oort clouds, scattered disks of debris around young stars, excesses of far infrared light suggesting distant cold material. Even observations of comets in other stellar systems hinted that the Oort cloud was not unique to our Sun but a common feature of planetary systems throughout the galaxy. Theoretical work complemented observations. Physicists developed better models of how gravity operated at extreme distances, how objects in highly elliptical orbits behaved, how external perturbations affected orbital stability over billions of years. Mathematicians refined techniques for calculating orbits from limited observations, for estimating uncertainties, for extracting maximum information from minimal data. Each advance in theory allowed better interpretation of the observations, tighter constraints on the cloud's properties. The investigation was patient work, accumulating data comet by comet, orbit by orbit, simulation by simulation. No single observation proved the Oort cloud's existence, but the weight of evidence built steadily. Each new long-period comet fit the pattern, each simulation confirmed the plausibility. Each chemical analysis supported the hypothesis of formation in the outer solar system. The pursuit became not a search for dramatic proof, but a gradual convergence of understanding, a slow construction of certainty from fragments of evidence. What the investigation revealed was a structure more complex and dynamic than originally imagined. The Oort cloud was not a static shell, but an evolving system, shaped by internal dynamics and external forces. It was vast beyond comprehension, yet intimately connected to the inner solar system through the comets it sent inward. It was ancient, preserving material from the solar system's birth, yet constantly changing as objects were lost to interstellar space or sent crashing into the inner planets. The pursuit of understanding had transformed an elegant hypothesis into a detailed, nuanced picture of a hidden frontier at the edge of reality. The Oort cloud might be invisible, but its existence leaves traces scattered throughout the inner solar system, fragments of evidence that astronomers have painstakingly collected and analysed. The most important data come from the comets themselves, those rare individuals nudged from distant orbits and sent falling sunward, their journeys providing the only direct samples we have from the hidden reservoir at the edge of the solar system. Halley's Comet, though a short-period visitor from the Kuiper belt rather than the Oort cloud, established the template for understanding cometary behaviour. When Edmund Halley calculated in 1705 that comets seen in 1531, 1607, and 1682 were the same object returning, he proved that comets were not random atmospheric phenomena, but predictable members of the solar system. His work showed that comets followed elliptical orbits, bound by gravity, obeying the same laws as planets. This foundation made it possible, centuries later, to trace long-period comets back to their distant source. Among the most spectacular long-period comets was Hale-Bopp, discovered in 1995. This comet's orbit indicated an origin in the Oort cloud, with an aphelion around 370 astronomical units from the Sun. Hale-Bopp became one of the brightest comets of the 20th century, visible to the naked eye for 18 months, its twin tails of dust and ionized gas stretching across the sky. Spectroscopic analysis revealed a rich chemistry, including water, carbon monoxide, methane, ammonia, and complex organic compounds, a snapshot of the materials present in the early outer solar system. Comet Hyakutake, which passed very close to Earth in 1996, provided even more detailed data. Because of its proximity, astronomers could study its composition with unprecedented precision. They detected not only the expected volatiles, but also ethane, methanol, and other organic molecules. The isotopic ratios of hydrogen, carbon, and nitrogen in Hyakutake's outgassing match predictions for material formed in the cold outer regions of the protoplanetary disk, supporting the theory that Oort cloud objects originated beyond the giant planets. More recently, comets like Ison and Lovejoy have added to the dataset. Ison, discovered in 2012, was particularly intriguing because its orbit suggested it might be making its first visit to the inner solar system, falling inward from the Oort cloud for the first time after billions of years in cold storage. Such dynamically new comets are especially valuable because they carry pristine material, unchanged by previous passages near the Sun. Though Ison disintegrated during its close approach, observations before its breakup provided data about the structure and composition of Oort cloud objects. The statistical distribution of comet orbits forms another crucial piece of data. When astronomers plot the aphelia of long-period comets, they find a clustering around 20,000 astronomical units, with a tail extending outward to 50,000 or more. This distribution matches what models predict for objects originating in the Oort cloud and perturbed by stellar passages or galactic tides. The randomness of the comet's arrival directions coming equally from all parts of the sky, rather than being confined to the ecliptic plane, further supports a spherical source region. The rate at which new long-period comets are discovered also provides constraints. Astronomers detect perhaps 1 or 2 new long-period comets per year on average, though the rate varies depending on observational resources and the comet's brightness. From this discovery rate, and accounting for comets too faint to detect, astronomers can estimate how many comets are being perturbed from the Oort cloud each year. These estimates, combined with models of how often perturbations occur, allow calculations of the cloud's total population, generally placed at trillions of objects larger than 1 kilometre across. Data from spacecraft missions to comets have revealed details invisible from Earth. When Giotto flew past Halley's Comet, it showed that the nucleus was not a smooth snowball, but an irregular, porous object with an extremely dark surface, darker than coal, covered in organic compounds that had been processed by cosmic radiation. Rosetta's study of Comet 67P revealed a layered structure, suggesting the comet formed from smaller pieces that gently aggregated rather than condensing as a single object. These insights into cometary structure inform understanding of how Oort cloud objects formed and evolved. Chemical analysis of cometary material has compared the isotopic signatures of water ice in comets to water on Earth. Some comets showed deuterium to hydrogen ratios similar to Earth's oceans, suggesting they could have delivered water to our planet during the heavy bombardment period. Others show different ratios, indicating a diverse population with varied formation locations. This diversity supports models showing that the Oort cloud contains objects scattered from different distances in the original protoplanetary disk, each carrying the chemical fingerprint of its birthplace. The discovery of interstellar objects like Oumuamua and Comet Borisov passing through the solar system has provided comparative data. These visitors from other stellar systems show some similarities to our comets, but also differences, helping astronomers understand what is universal about comet formation and what might be specific to our solar system. The fact that other systems apparently have their own populations of icy bodies supports the idea that Oort clouds are common around stars. Measurements of the solar system's mass have also contributed data. By carefully tracking the orbits of planets and spacecraft, astronomers can calculate the total mass of the solar system. Comparing this to the mass of visible objects shows there is no significant missing mass that could be hidden in the Oort cloud. This constrains the cloud's population, indicating it contains perhaps a few Earth masses of material at most, far less than the planets, but still a substantial reservoir of comets. Long-term monitoring of the Sun's motion through space has revealed encounters with nearby stars. Astronomers can calculate that Gliese 710 passed within about 1 light-year of the Sun roughly 70,000 years ago, close enough to have significantly perturbed Oort cloud orbits. Other stars will make similar close approaches in the future. These stellar encounters provide natural experiments, perturbing the cloud in ways that send comets inward, allowing astronomers to observe the effects and refine models of the cloud's structure and dynamics. The data accumulated over decades of observation forms a mosaic. No single piece proves the Oort cloud's existence definitively, but together they create an overwhelming case. The comets arrive from random directions, their orbits trace back to distant aphelia, their chemistry matches expectations for objects formed in the outer solar system, their arrival rate fits models of a vast reservoir, and the theoretical framework explains all of it coherently. The clues and fragments carefully gathered and analysed have built a detailed picture of an invisible structure, demonstrating that even at the edge of reality, evidence can illuminate what the eye cannot see. Beneath the surface of the Oort cloud's existence lies a truth more profound than its mere presence at the edge of the solar system. This truth transforms the cloud from a curiosity into something essential, something that connects us to the deepest history of our cosmic home. The Oort cloud is not simply a reservoir of comets, but a time capsule, a frozen archive preserving materials from the solar system's birth with a fidelity that nothing in the inner system can match. When the solar system formed 4.5 billion years ago, the protoplanetary disk was filled with materials that would never appear again in quite the same form. The disk contained the raw ingredients from which everything would be built, a mixture of hydrogen and helium from the Big Bang, heavier elements forged in previous generations of stars, organic molecules synthesized in interstellar clouds, ice grains coated with complex chemistry. This primordial mixture held the potential for planets, for atmospheres, for oceans, perhaps even for life itself. As planets formed and evolved, they processed these materials. Earth's interior melted and differentiated, separating into core, mantle, and crust. Volcanic activity brought new rocks to the surface. Plate tectonics recycled material through subduction and spreading. Atmospheric chemistry changed as life emerged, and photosynthesis began producing oxygen. By now, 4.5 billion years later, almost nothing on Earth remains in its original form from the solar system's birth. Everything has been transformed, processed, mixed, altered by geological and biological activity. The same is true throughout the inner solar system. Mars once had liquid water and a thicker atmosphere, but lost them over billions of years. Venus experienced a runaway greenhouse effect that transformed its surface. Mercury's proximity to the Sun subjected it to extreme heating. Even asteroids, though less geologically active, have been heated by radioactive decay, fractured by impacts, altered by exposure to solar radiation. Nowhere in the inner solar system can we find unaltered samples of the original protoplanetary disk, except in the Oort cloud. The icy bodies scattered to those extreme distances never experienced the warmth that drives geological activity. They never melted, never differentiated, never erupted or weathered. The cold at those distances, just a few degrees above absolute zero, is so extreme that chemical reactions essentially stop. Water ice remains solid, volatile compounds stay frozen, organic molecules lie dormant. For billions of years, these objects have drifted unchanged, preserving within them the exact chemistry present when they formed. This makes every Oort cloud comet a messenger from the past, carrying information about conditions in the early solar system. When a comet is perturbed and begins its fall toward the sun, it carries with it frozen water ice that condensed from the protoplanetary disk, carbon compounds that formed in interstellar space before the sun was born, silicate grains that may have been forged in supernova explosions billions of years ago. To analyze a comet's composition is to read a record of the solar system's birth. The deeper mystery is what this archive might tell us about our origins. Some theories propose that Earth's water was delivered by comets during the late heavy bombardment period, roughly 4 billion years ago, when the inner solar system experienced intense impacts. If true, then the oceans we know, the water that makes up most of our bodies, might have originated in the Oort cloud. Every raindrop, every wave, every tear could be traced back to ice that spent billions of years at the edge of reality before falling inward to become part of Earth. More provocatively, some scientists suggest that comets might have delivered the organic molecules that became the precursors to life. Spectroscopic analysis of comets has revealed amino acids, the building blocks of proteins, along with other complex organic compounds. These molecules form naturally in space through chemistry, driven by radiation and cosmic rays. If comets brought such molecules to the early Earth, they might have seeded the chemistry that eventually led to the emergence of life. The Oort cloud, in this view, is not just an archive, but a library of life's potential ingredients. This possibility elevates the cloud's significance beyond mere astronomy. If the materials necessary for life exist throughout the Oort cloud, and if similar clouds surround other stars, then the galaxy might be full of such frozen libraries, each one containing the chemical seeds of potential biology. Comets from one stellar system might even cross into another, mixing materials across interstellar distances. Life's origins might not be confined to individual planets, but connected through a galactic network of cometary exchange. The hidden truth also extends to what the Oort cloud reveals about solar system formation itself. The very existence of the cloud, its structure and population, tells us about the dynamics of the early solar system. The scattering of objects to such distant orbits required powerful gravitational interactions, which in turn tells us about when and where the giant planets formed, how they migrated, how they rearranged the architecture of the young system. The cloud is a record not just of material, but of process, of the violence and beauty of planetary birth. Studying the cloud also illuminates the role of chance in solar system evolution. Which objects were scattered outward, and which remained in the inner system was partly random, depending on the exact timing and geometry of gravitational encounters. A small difference in trajectory could mean the difference between becoming a comet in the Oort cloud or a piece of Earth. This randomness suggests that the current configuration of the solar system is just one possibility among many that could have emerged from the same initial conditions. The deeper mystery includes questions we cannot yet answer. What is the full inventory of materials in the Oort cloud? Are there large bodies, perhaps even dwarf planets or rogue planets hidden in the darkness? What can the isotopic signatures of cloud objects tell us about the galactic environment when the sun formed? How diverse is the cloud's population, and what does that diversity reveal about mixing processes in the protoplanetary disk? Each question points toward knowledge we can imagine, but not yet access. There is something profound in knowing that such a treasure trove of information exists at the edge of the solar system, waiting. The Oort cloud is not an empty frontier, but a full archive, containing more data about our origins than we have yet learned to read. Every comet that falls inward offers a chance to sample that archive, to extract another fragment of the record, to learn something new about where we came from and how we came to be. The hidden truth is this: The edge of the solar system is also the beginning of the solar system. The Oort cloud holds the past in suspension, unchanged and patient, a library of creation preserved in ice. To reach it, to study it, to understand what it contains would be to read the opening chapters of our own story, to see ourselves not as we are now, but as we were in potential before planets formed, before life emerged, when everything was still frozen possibility drifting in the dark. The mystery is not that the cloud exists, but what it knows, what it remembers, what it could teach us if we could learn to ask the right questions and reach far enough to find the answers. On August 25th, 2012, the trajectory of human exploration reached a milestone that would forever change how we understood the solar system's boundaries. Voyager 1, a spacecraft launched in 1977, crossed the heliopause and entered interstellar space. This was not merely a technical achievement, but a paradigm shift, a moment when our physical presence finally touched the edge we had only theorized about, when the abstract became tangible, when the boundary between the solar system and the galaxy ceased to be a line on a diagram and became a place where human-made instruments recorded the transition. Voyager 1 had been travelling outward for 35 years, moving at roughly 17 kilometers per second relative to the Sun. It had passed Jupiter in 1979, Saturn in 1980, sending back revolutionary images of these giant worlds and their moons. But its primary mission had always been to keep going, to venture beyond the realm of planets into the unknown. By the early 2000s, scientists tracking Voyager's data began noticing subtle changes that suggested the spacecraft was approaching something significant. The heliopause is the boundary where the solar wind, that stream of charged particles flowing outward from the Sun, meets the interstellar medium, the diffuse plasma that fills the space between stars. Inside the heliopause, particles from the Sun dominate. Outside, particles from the wider galaxy take over. The transition is not instantaneous, but occurs over a region called the heliosheath, where the solar wind slows and compresses as it encounters the resistance of interstellar space. Voyager's instruments detected the first signs of this transition years before the actual crossing. The intensity of galactic cosmic rays, high-energy particles from distant supernovae and other violent events began increasing. The density of solar wind particles began decreasing. The magnetic field carried outward by the solar wind showed signs of compression and turbulence. But the exact moment of crossing was difficult to pinpoint because the heliopause itself moves, breathing in and out with changes in solar activity, shifting position as the Sun's output varies. Scientists debated when the crossing had occurred. Some signatures suggested Voyager had crossed in July 2012. Others pointed to August. The team finally settled on August 25th, based on a sudden drop in solar particles and a simultaneous increase in galactic cosmic rays. At that moment, roughly 123 astronomical units from the Sun, 18 billion kilometers from Earth, Voyager 1 left the region dominated by our star and entered the space between stars. The paradigm shift this represented was profound. For the first time, humanity had physical evidence of what the edge felt like, not just theoretical models, but actual measurements from instruments on the other side. The data showed that the boundary was real, but subtle, measurable but not visually distinct. If a human had been aboard Voyager, they would have seen no change, no wall or barrier, just the same darkness and distant stars. The edge existed in particle densities and magnetic field strengths, detectable by instruments but invisible to the eye. This shifted how scientists thought about boundaries. The heliopause was clearly significant, marking a genuine transition from solar to galactic dominance, and yet it was not the end of the solar system in the way earlier generations might have imagined. Beyond the heliopause lay the Oort cloud, still bound by the Sun's gravity, still part of the solar family even though the solar wind no longer reached it. The paradigm shift was recognizing that the solar system had multiple edges, layers of boundaries, each marking a different kind of transition. Voyager's crossing also transformed the abstract into the personal. For decades, the heliosphere and heliopause had been concepts in textbooks and research papers. Now they were places where something human existed, where our technology operated, where data flowed back across the vast distance to remind us that we had reached beyond ourselves. The spacecraft carried the golden record, a time capsule containing sounds and images from Earth, greetings in multiple languages, music spanning human cultures. That record was now in interstellar space, a message in a bottle cast into the cosmic ocean. The paradigm shift extended to how we understood our place in the cosmos. The solar system was no longer a discrete island with clear borders, but a complex structure embedded in the galaxy. The sun carved out a bubble in the interstellar medium through its solar wind, but that bubble was porous, constantly interacting with its surroundings, shrinking and expanding, shaped by forces beyond our control. We were not separate from the galaxy, but part of it, connected through exchanges of matter and energy. This realization carried philosophical weight. If the solar system's edge was so ambiguous, so layered, so dependent on what you measured and where you stood, then what did it mean to belong? Voyager 1 was now in interstellar space, yet it was still gravitationally bound to the sun, still technically part of the solar system. It existed in two realms at once, both inside and outside, both ours and not ours. This ambiguity reflected a deeper truth, that all boundaries are human constructs, useful for organization but not absolute in nature. The turning point also inspired new questions. If Voyager could cross the heliopause, could we eventually send missions to the Oort cloud itself? The distances were staggering, thousands of times farther than Voyager had traveled, but the principle was proven. We could build spacecraft that lasted decades, that carried power sources and instruments across vast gulfs, that sent back data from beyond the familiar. The technology existed in primitive form. What remained was vision, resources, and time. Scientists began designing conceptual missions to the Oort cloud, propulsion systems using nuclear power or solar sails, instruments that could detect and study the cloud's icy bodies, communication systems that could maintain contact across light years. These designs remained speculative, but Voyager's success showed they were not fantasy. Humanity had demonstrated the ability to reach the edge of the solar wind. Reaching the edge of the sun's gravity was a difference in degree, not in kind. The paradigm shift Voyager 1 represented was ultimately about possibility. Before its crossing, interstellar space was purely theoretical, a concept without physical reality for humans. After, it became a place, a region we had touched, a frontier we had crossed. This transformation from abstract to concrete changed how we imagined the future. If we could reach the heliopause in 1 generation, what might we reach in 10, in 100? The Oort cloud, now invisible and untouchable, might one day be as accessible as the planet seemed when Voyager was launched. As the data from Voyager 1 continued to stream back, analysed by scientists around the world, the turning point crystallized into understanding. The solar system was larger and stranger than we had known. Its edges were multiple and ambiguous. Its relationship to the galaxy was intimate and ongoing. And humanity, through one small spacecraft carrying instruments and a golden record, had crossed one of those edges and proven that the boundary between here and there, between known and unknown, between solar and galactic, was real but permeable, significant but not final, a threshold we could cross and, having crossed, imagine crossing again. The moment Voyager 1 crossed into interstellar space, the ripples began spreading through scientific communities, through educational institutions, through public consciousness. This was not a discovery that changed daily life in obvious ways. No new technology emerged, no immediate applications appeared, but something subtler and more profound occurred. The way humanity understood its cosmic address shifted. We were no longer just residents of Earth or even just citizens of a solar system. We had become, in however small a way, participants in interstellar space. The immediate consequence in the scientific community was a surge of renewed attention to the outer solar system and the regions beyond. Researchers who had focused on planets or asteroids began considering the Oort cloud with fresh seriousness. If we could send a probe across the heliopause, could we design missions to reach the inner edge of the cloud? The question was no longer purely theoretical. Voyager had proven that spacecraft could survive for decades in the harsh environment beyond the planets, that power sources could last, that communication could be maintained across billions of kilometers. Funding agencies began receiving proposals for new missions targeting the outer reaches. Some suggested spacecraft that would fly faster than Voyager, using more efficient propulsion or gravity assists arranged to maximize velocity. Others proposed missions that would not travel as far, but would focus on detecting Oort cloud objects from within the solar system, using sensitive instruments to spot the faint signatures of distant comets before they were perturbed inward. The tone of these proposals changed after Voyager's crossing. What had been speculative became plausible. In education, the crossing provided a tangible example for teaching about boundaries and exploration. Students who had learned about the solar system as a collection of planets orbiting within a relatively small space now had to grapple with a more complex picture. The heliopause became a new landmark in the curriculum, joining the asteroid belt and Kuiper belt as regions that defined the architecture of our cosmic home. Teachers used Voyager's journey to illustrate persistence, to show how patient exploration could achieve what seemed impossible. The public response was quieter but meaningful. News of the crossing made headlines, though it competed with more immediate terrestrial concerns. But for those who paid attention, there was a sense of milestone, of humanity reaching a new frontier. Social media filled with images of Voyager, with diagrams showing its position relative to the Sun and Earth, with reflections on what it meant to have something human existing in the space between stars. The golden record, carrying sounds and images from Earth, took on new symbolism as it crossed the boundary. There were philosophical consequences as well. The crossing forced a reckoning with what we meant by the solar system's edge. If the heliopause marked where the solar wind ended, but the Oort cloud extended far beyond that, and the sun's gravity reached farther still, then where did the solar system truly terminate? The answer became clear. There was no single edge, no definitive boundary. Instead, there were multiple transitions, each marking the end of one kind of influence and the beginning of another. This realization had implications for how we thought about other stellar systems. If our sun's influence extended so far in so many forms, then other stars must do the same. The galaxy was not a collection of isolated systems, but a network of overlapping influences, with heliospheres touching, or even interpenetrating, with Oort clouds possibly merging at their outer edges, where gravitational binding became ambiguous. The space between stars was not empty, but filled with these extended atmospheres and halos, a complex ecology of stellar influence. The crossing also prompted reflection on timescales. Voyager 1 had taken 35 years to reach the heliopause, travelling at 17 kilometers per second. At that speed, it would take roughly 300 more years to reach the inner edge of the Oort cloud, and perhaps 30,000 years to cross the cloud entirely. These numbers were sobering. They illustrated the vastness of the solar system's outer reaches, the gulf between where we were and where the true edge might lie. Human exploration on these scales would require technologies and perspectives radically different from what we possessed. In scientific conferences following the crossing, researchers presented new models of the heliosphere's structure, refined by Voyager's data. They showed how the heliopause was not spherical but asymmetrical, compressed in the direction the sun moved through the galaxy and elongated in the opposite direction, creating a comet-like shape. This asymmetry had consequences for understanding how the solar system interacted with the interstellar medium, how cosmic rays penetrated the heliosphere, how the solar wind carved out its bubble in the galactic plasma. The data from Voyager also revealed unexpected features. The magnetic field in the interstellar medium was stronger than predicted. The density of neutral atoms was higher. The boundary region was more turbulent. Each of these findings required adjustments to existing models, showing that even after decades of theoretical work, the actual boundary still held surprises. This was a reminder that reality always exceeded our models, that the universe retained capacity to astonish, even when we thought we understood. Artists and writers drew inspiration from the crossing. Science fiction stories imagined what might happen when Voyager was eventually found by some other civilization millions of years in the future. drifting through interstellar space with its golden record still attached. Visual artists created works depicting the moment of crossing, trying to capture what was invisible, giving form to the boundary through metaphor and imagination. The crossing became a cultural touchstone, a shared human achievement that transcended national boundaries and connected people through a common sense of exploration. The consequence for how we understood the Oort cloud was significant. Voyager's crossing proved that reaching beyond the planets was possible, but it also highlighted how far we still had to go. The heliopause was one edge, tangible and measurable. The Oort cloud represented another edge, farther and more mysterious. Between them lay a gulf that current technology could not quickly cross, and yet Voyager's success planted the idea that future generations might succeed where we had only just begun. Perhaps the most profound immediate consequence was psychological. Before Voyager crossed, interstellar space was other, foreign, beyond human reach in any practical sense. After, it became a place we inhabited, if only through a single small spacecraft. This shift in perspective was subtle but real. The galaxy felt closer, more accessible, less alien. We had taken a step beyond our stellar home, and that step, however small, changed what seemed possible. The ripple from that moment would continue, spreading outward, through science, through culture, through imagination, reshaping how we understood not just where the solar system ended, but where humanity's future might lead. The discovery and exploration of the Oort cloud, culminating in Voyager's crossing of the heliopause, sent echoes through time that reshaped our understanding, not just of our own solar system, but of planetary systems throughout the galaxy. What began as Jan Oort's elegant solution to a puzzle about cometary orbits evolved into a fundamental component of how we understood stellar system architecture, influencing fields from planetary formation theory to astrobiology, from stellar dynamics to the search for life beyond Earth. One of the most significant long-term impacts was on our models of how planetary systems form and evolve. The recognition that material could be scattered to extreme distances during a solar system's youth, creating vast reservoirs of primordial ice and rock, changed how astronomers interpreted observations of young stellar systems. When telescopes detected disks of material around newborn stars, scientists began looking for evidence of scattering processes, for gaps and structures that might indicate giant planets were flinging material outward, creating the beginnings of Oort-like clouds. This led to a profound realization. Oort clouds might be common, perhaps even universal, around stars with planetary systems. If gravitational scattering was a natural consequence of planet formation, then most stars should be surrounded by their own halos of icy debris. This transformed the Oort cloud from a peculiarity of our solar system into a fundamental feature of how stellar systems work. The galaxy might contain trillions of such clouds, each one a frozen reservoir surrounding its star, each one a time capsule preserving materials from planetary birth. The impact on astrobiology was equally significant. If Oort clouds were common, and if they could deliver water and organic molecules to planets through cometary impacts, then the building blocks of life might be distributed throughout stellar systems in standardized ways. A rocky planet in the habitable zone of its star might receive deliveries from its system's Oort cloud, seeding its surface with the chemistry needed for biology to emerge. This suggested that life's ingredients were not rare or special, but routine consequences of planetary system evolution. Some researchers took this idea further, proposing that Oort clouds might facilitate panspermia, the transfer of life or its precursors between stellar systems. If comets could be ejected from one system's Oort cloud and captured by another, they might carry not just chemistry, but potentially even dormant microbial life across interstellar distances. This remained speculative, but the recognition that Oort clouds made stellar systems porous to exchange of material opened new possibilities for how life might spread through the galaxy. The study of stellar dynamics was transformed by considering how stars passing near each other could perturb Oort clouds. Astronomers realized that close stellar encounters, while rare for any individual star, were common enough over galactic timescales to significantly affect cloud populations. These encounters could trigger showers of comets, periods when the inner solar system received far more impacts than usual. Some researchers propose that past encounters might correlate with mass extinction events in Earth's history, though evidence for such connections remained controversial. Understanding the Oort cloud also influenced how we thought about the age and stability of the solar system. The fact that the cloud still existed after 4.5 billion years, despite constant perturbations from passing stars and galactic tides, showed that it was more stable than early models suggested. This stability implied that the outer solar system had been relatively quiescent, that catastrophic disruptions had been rare. The cloud became a witness to the solar system's long-term stability, its existence proof that we lived in a relatively calm galactic neighbourhood. The impact on public understanding of the cosmos was gradual but real. Before Oort proposed his cloud, most people imagined the solar system as extending only to the planets, perhaps to Pluto. After, the solar system's scale expanded dramatically in popular conception. Documentaries and educational materials began depicting the cloud, using graphics and animations to show its vast spherical extent. This changed how people visualized our place in space, showing that we lived not just on a planet or in a planetary system, but within multiple nested structures, each larger than the last. The philosophical impact echoed through decades. The Oort cloud became a symbol for how much we did not know about even our immediate cosmic environment. It represented the invisible, the inferred, the accepted, without proof. This had implications for how we thought about knowledge itself. If we could be confident about something we had never observed, based purely on indirect evidence and mathematical modelling, what did that say about the nature of understanding? The cloud became a test case in epistemology, in the philosophy of science, in debates about what it meant to know something. In literature and art, the Oort cloud provided a new frontier for imagination. Science fiction writers placed stories there, using its vast distances and hidden nature as settings for mysteries and adventures. Artists created works inspired by its invisible presence, trying to give visual form to something known only through its effects. The cloud entered cultural consciousness, not as a specific place, but as a concept, a representation of edges and boundaries, and the unknown that lay beyond. The impact on how we understood comets themselves was profound. They were no longer just celestial wanderers or omens, but became recognized as messengers from the solar system's edge, samples from a time capsule that surrounded us. Every comet that blazed through the inner solar system was understood as a visitor from that distant halo, carrying information about conditions in the protoplanetary disk. This elevated cometary science from a niche specialty to a crucial field for understanding solar system origins. Over time, the echoes of the Oort cloud's discovery reached into increasingly distant fields. Climate scientists considered how past cometary impacts might have affected Earth's climate history. Geologists looked for evidence of impact events that might correlate with stellar encounters perturbing the cloud. Chemists studied the organic compounds found in comets to understand prebiotic chemistry. The cloud's influence spread through interconnected disciplines, each finding new relevance in this structure at the edge of the solar system. Perhaps the deepest impact was on how we understood edges themselves. The Oort cloud showed that boundaries in nature were not sharp lines but gradients, that edges were not endings but transitions, that what seemed like the limit of one domain was really the beginning of another. This insight, learned from studying the solar system's edge, applied to countless other contexts in science and beyond. It became a metaphor for how reality worked, how systems interfaced, how belonging and separation were not opposites but parts of a continuum. The echoes continue even now, rippling forward into future research. Each new observation of a long-period comet adds data. Each refinement of models adds understanding. Each advance in telescope technology brings the possibility of directly observing Oort cloud objects closer. The impact of Oort's original insight, proposed over 70 years ago, continues to shape how we explore, how we theorize, how we imagine the cosmos. The edge of the solar system, once thought to be Neptune or Pluto, has become a frontier that extends almost to the nearest stars, a boundary that defines not just where we are, but how we understand our place in the galaxy's vast structure. Behind every discovery about the Oort cloud, behind every calculation and observation, stand individuals whose curiosity and dedication pushed human understanding outward. These are the dreamers, the astronomers who spent careers studying invisible structures, the engineers who designed spacecraft to explore beyond the planets, the scientists who stared at data until patterns emerged. Their stories are woven into the story of the cloud itself, reminding us that cosmic exploration is ultimately a human endeavour, driven by qualities that have nothing to do with equations and everything to do with wonder. Jan Oort himself embodies this human element. Born in 1900 in the Netherlands, he came of age during a golden era of astronomy, when the nature of the Milky Way was being revealed and the scale of the universe was expanding beyond imagination. Oort's early work focused on stellar motions, on understanding how stars orbited the galactic centre. He had a gift for extracting large-scale patterns from detailed observations, for seeing the forest rather than just the trees. This same gift allowed him to look at scattered cometary orbits and infer the existence of a vast spherical reservoir. What drove Oort was not just intellectual curiosity, but a deeper sense of wonder about the cosmos. He understood that astronomy was not merely about cataloguing objects, but about understanding structure, about seeing how things connected and why they existed in particular configurations. When he proposed the cloud that would bear his name, he was not seeking fame, but trying to make sense of a genuine puzzle. The fact that his solution required postulating something invisible, something that might never be directly observed, did not deter him. He trusted the mathematics and the patterns in the data. Oort lived long enough to see his hypothesis gain widespread acceptance, to watch as more comets were discovered that fit his predictions, to witness the beginning of space exploration that would eventually send Voyager beyond the planets. He died in 1992 at the age of 92, having spent his entire adult life thinking about the structure of galaxies and solar systems. His legacy was not just the cloud itself, but the demonstration that patient, careful reasoning could reveal truths about regions far beyond human reach. Others who contributed to understanding the cloud brought different qualities. Fred Whipple, the American astronomer who proposed the dirty snowball model of comets in 1950, showed that comets were not loose collections of dust, but solid nuclei of ice and rock. This insight was crucial for understanding how Oort cloud objects could remain intact over billions of years. Whipple combined theoretical work with observational dedication, spending decades studying meteors and comets, always returning to the question of what these objects were made of and where they came from. The engineers and scientists behind Voyager represent another aspect of the human element. When Voyager 1 and 2 were designed in the 1970s, no one knew if they would survive long enough to reach the heliopause. The spacecraft were built with redundancy, with systems that could compensate for failures, with power sources designed to last decades. The team that built Voyager included hundreds of people, each contributing specialized knowledge, each believing that humanity should reach beyond the familiar, even though the journey would take longer than most careers, longer than most lives. Ed Stone, who served as Voyager's project scientist from before launch through the heliopause crossing and beyond, embodied the patience required for such long-term exploration. Stone was 36 years old when Voyager launched. He was 76 when Voyager 1 crossed into interstellar space. He dedicated his entire professional life to this mission, analysing data, giving presentations, keeping public attention focused on spacecraft that were billions of kilometres away. His commitment represented a belief that some questions were worth entire lifetimes to answer. The scientists who studied cometary orbits over decades, compiling catalogues and calculating trajectories, were also dreamers in their own way. This work was often unglamorous, requiring meticulous attention to detail, night after night of observation, careful measurement of positions against background stars. Brian Marsden at the Harvard-Smithsonian Center for Astrophysics spent decades calculating and cataloguing cometary orbits, building the database that allowed patterns to emerge. His work provided the observational foundation that supported theoretical models of the Oort cloud. Women contributed crucially to this work, though their roles were often overlooked. Carolyn Shoemaker discovered more comets than anyone else in history, over 800, many of them long-period visitors from the Oort cloud. Her observations, made using photographic plates and later digital images, added crucial data points to understanding the cloud's population and dynamics. She brought to the work not just skill, but persistence, spending night after night scanning images for the faint smudges that might indicate new comets. The human element also includes those who translated scientific findings into public understanding. Carl Sagan, though primarily known for other work, helped bring the Oort cloud into popular consciousness through his writing and television programs. He had a gift for making cosmic scales comprehensible, for helping people visualize structures like the cloud that existed beyond direct experience. His ability to convey wonder without sacrificing accuracy inspired generations to think about the solar system's outer reaches. Graduate students and postdoctoral researchers, often unnamed in popular accounts, contributed essential work. They ran computer simulations of solar system formation, modeled the dynamics of objects in distant orbits, analyzed spectroscopic data from comets. Their dissertations and papers built the detailed understanding that supported the broad picture. Many never achieved fame or even tenure, but their work added bricks to the growing edifice of knowledge about the cloud. Amateur astronomers played a role as well. Comet discovery was one field where amateurs could still contribute meaningfully, scanning the skies with telescopes in their backyards or on remote hillsides. When someone like Yuji Hyakutake or Alan Hale and Thomas Bopp discovered comets later shown to originate from the Oort cloud, they added to the body of evidence while demonstrating that exploration was not just for professionals, but for anyone with dedication and patience. What united all these individuals was a willingness to spend time and effort on questions whose answers might not arrive in their lifetimes. The Oort cloud demanded this kind of patience. It could not be studied quickly. Understanding accumulated slowly, orbit by orbit, observation by observation, over decades and generations. The dreamers who devoted themselves to this work accepted that they were part of a larger project, that their contributions would be built upon by others, that the full picture might only emerge long after they were gone. There was also the human quality of stubbornness, of refusing to accept ignorance about something just because it was difficult to study. When people asked why it mattered to understand a region no human would ever visit, the dreamers had answers. It mattered because the cloud was part of our cosmic home. It mattered because understanding origins required studying preserved materials. It mattered because humans were curious creatures who needed to know what lay beyond every horizon. The practical justifications came later. First came the drive to know. The human element in the Oort cloud story reminds us that science is not an impersonal accumulation of facts, but a deeply human activity. It requires imagination to propose invisible structures. It requires patience to gather evidence over lifetimes. It requires courage to dedicate careers to questions that might never be fully answered. It requires wonder, the kind of wonder that makes someone stare at the night sky and ask what lies in the darkness between the stars. What holds the comets before they fall inward? What stories are written in ice at the edge of reality? As we think about these dreamers, lying here in the quiet, we can recognize something of ourselves in them. The same curiosity that drove them to study the Oort cloud is present in anyone who has ever wondered about the cosmos, who has looked up and asked questions, who has imagined what might exist beyond direct perception. The dreamers were not superhuman, but simply humans who followed their wonder wherever it led, even to the invisible edge of the solar system, even to structures they would never touch but could know through patient observation and careful thought. Not everyone accepted the Oort cloud without skepticism. Throughout its history, from Oort's original proposal to the present day, the hypothesis has faced opposition, questions and alternative explanations. This skepticism was not mere contrarianism, but represented the proper functioning of science, the necessary process of testing ideas against evidence, of demanding proof before accepting claims, especially claims about something that could not be directly observed. The battle for truth about the Oort cloud was fought not with weapons, but with observations, mathematics, and the patient accumulation of evidence that gradually convinced even the skeptics. The earliest opposition came from astronomers who felt uncomfortable accepting a structure based purely on inference. They argued that explaining cometary orbits required only that some reservoir existed, not that it had to be spherical, not that it had to extend to such extreme distances. Perhaps comets originated from multiple sources, some from the Kuiper belt, others from disrupted planets or captured interstellar objects. Why postulate a single vast invisible cloud when simpler explanations might suffice? Some critics pointed to the lack of direct detections. If the Oort cloud contained trillions of objects, surely at least a few should be observable, even at extreme distances. The fact that not a single cloud object had been detected in its native orbit was troubling. Perhaps the cloud did not exist at all, and comets had different origins entirely. This argument was difficult to counter, because it was technically correct. The cloud remained invisible, and invisibility always left room for doubt. Others questioned the stability of such a structure. Computer models in the early decades after Oort's proposal showed that objects in the outer cloud would be easily perturbed by passing stars. Wouldn't the cloud have been disrupted and scattered over 4.5 billion years? How could it still exist? Some scientists calculated that the cloud should have lost most of its population, that the comets we see today should have exhausted the reservoir long ago. If the cloud was real, these critics argued, we needed better explanations for how it remained stable. Alternative theories emerged. One proposal suggested that comets formed not in our solar system, but in interstellar space, perhaps in giant molecular clouds, where conditions allowed ice to accumulate. These interstellar comets might occasionally pass through our solar system, creating the illusion of a bound population, when in fact the objects were transient visitors. Another theory proposed that comets originated from a planet that had been destroyed, its fragments scattered into distant orbits. Each alternative had to be taken seriously, examined, compared against observations. The debate intensified when astronomers began discovering large objects in the Kuiper belt in the 1990s. Here was a real population of icy bodies beyond Neptune, directly observable, clearly existing. Some skeptics argued that the Kuiper belt might explain all comets, that there was no need to postulate an additional unseen reservoir. Perhaps what Oort had interpreted as evidence for a distant spherical cloud could be explained by dynamics within the Kuiper belt, by objects being scattered into elongated orbits that mimicked Oort cloud origins. Defenders of the Oort cloud hypothesis responded with careful analysis. They showed that Kuiper belt objects had different orbital characteristics than long-period comets. Kuiper belt objects were concentrated near the ecliptic plane, while long-period comets arrived from all directions. The orbital dynamics were distinct. The chemistry, when measured, showed differences. The Kuiper belt was real and important, but it did not explain everything. The Oort cloud remained necessary to account for the full range of observations. The battle for truth required mounting evidence from multiple lines of inquiry. Spectroscopic studies of comets showed they carried materials consistent with formation in the outer solar system, supporting the scattering hypothesis. Computer simulations grew more sophisticated, showing that a population of scattered objects could indeed remain stable for billions of years despite perturbations, as long as the original population was large enough. Statistical analyses of cometary orbits showed patterns that were difficult to explain without a spherical source region. Some opposition came from concerns about claims exceeding evidence. Scientists, rightly cautious about accepting invisible structures, worried that the Oort cloud could become unfalsifiable, that any observation could be explained by adjusting parameters of the cloud's structure or population. If the cloud could not be directly observed, and if any cometary orbit could be attributed to it, how could the hypothesis ever be proven wrong? This was a legitimate epistemological concern about what counted as scientific knowledge. The response was to show that the Oort cloud hypothesis made specific predictions that could be tested. It predicted that long-period comets should arrive from random directions. It predicted certain distributions of orbital energies. It predicted that comets should show minimal processing from repeated solar approaches, indicating they were falling inward for the first time. Each prediction could be tested against observations, and when observations matched predictions, confidence in the hypothesis grew. The cloud might be invisible, but it was not unfalsifiable. Opposition also emerged from planetary scientists, who felt the Oort cloud diverted attention and resources from more accessible regions of the solar system. Why spend effort modelling an invisible structure when the Kuiper belt was observable and rich with scientific potential? Why discuss missions to the Oort cloud when we had barely begun exploring the outer planets? This was less about truth and more about priorities, but it reflected real tensions in how scientific communities allocated limited resources. Over time, the weight of evidence gradually converted most skeptics. The discovery of comets like Hale-Bopp and Hyakutake, with orbits clearly indicating extreme aphelia, added data points. The success of solar system formation models that naturally produced Oort clouds, as byproducts of planet formation, made the hypothesis more plausible. The crossing of Voyager into interstellar space, while not reaching the cloud itself, demonstrated that the outer solar system had real physical structures marking transitions and boundaries. Some opposition remained, even as consensus formed. A few astronomers continued to propose alternative scenarios, to question specific details of cloud structure or formation. This ongoing questioning was healthy, preventing the hypothesis from becoming dogma, keeping researchers honest about what was known versus what was assumed. Science worked best when ideas faced scrutiny, when even widely accepted hypotheses had to defend themselves against challenges. The battle for truth about the Oort cloud was never conclusively won because the cloud remained unobserved. What was won was a consensus that the hypothesis was the best available explanation for observed phenomena, that it fit the data better than alternatives, that it made sense within our broader understanding of solar system formation. This was how science typically worked, not through absolute proof, but through accumulating evidence that made one explanation more likely than others. In the end, the opposition served a valuable purpose. It forced defenders of the Oort cloud hypothesis to strengthen their arguments, to gather better data, to refine their models. It prevented premature acceptance of claims that could not be supported. It maintained scientific rigor at a time when the temptation might have been to accept an elegant idea without sufficient scrutiny. The skeptics, even when ultimately wrong about the cloud's non-existence, were right about the need for caution, for evidence, for testing. The battle for truth continues in subtler forms even now. Questions remain about the cloud's precise structure, its exact population, its formation mechanisms. Scientists still debate details while accepting the broad picture. This ongoing refinement represents science at its best, accepting what evidence supports while remaining open to revision if new data demands it. The Oort cloud exists in scientific consensus, not as absolute certainty, but as the most reasonable interpretation of available evidence, subject always to further investigation, always open to being proven wrong if better explanations emerge. The gradual acceptance of the Oort cloud's existence brought with it something deeper than scientific consensus. It brought an awakening, a shift in human consciousness about our place in the cosmos, about the nature of boundaries, about what it means to belong to a solar system. This awakening was not sudden, but accumulated slowly over decades, as the implications of the cloud's existence permeated through astronomy, philosophy, and culture, changing how we understood not just where the solar system ended, but what edges meant in a universe that seemed to resist every attempt to draw clear lines. The first aspect of this awakening was spatial. For most of human history, the cosmos had been small. The ancients saw a dome of stars overhead, close enough that gods might inhabit them. Even after Copernicus, even after we understood that Earth orbited the Sun rather than the reverse, the solar system remained compact in imagination. The planets were distant but countable, visible, knowable. Then came the Oort cloud, pushing the boundary outward by a factor of thousands, transforming the solar system from a neighborhood into something approaching the scale of interstellar distances. This spatial awakening changed how we visualized our cosmic home. We were not inhabitants of a tidy system of planets, but residents of a vast sphere, most of it empty, most of it dark, with the familiar planets clustered at the center like a small town surrounded by endless wilderness. The scale was humbling. If you could somehow see the Oort cloud and the solar system from outside, the planets would be invisible, indistinguishable from the sun, while the cloud would define the system's visible extent. We lived in the bright center of something unimaginably larger. The awakening was also temporal. The Oort cloud preserved materials from the solar system's birth, unchanged for 4.5 billion years. This meant that the past was not gone, but still present, frozen in orbit at the edge, waiting. Time became less linear and more layered. The present solar system, with its evolved planets and active sun, coexisted with the ancient solar system preserved in ice. To study the cloud was to study both now and then simultaneously, to recognize that different eras could exist side by side at different distances from the center. There was an awakening about interconnection. The Oort cloud showed that nothing in the solar system was truly separate. Material scattered outward during planet formation remained connected through gravity. Comets fell inward, mixing edge with center. The sun's influence reached across light years, binding everything into a coherent system. This challenged notions of isolation, showing that even at cosmic scales, everything was linked. Everything influenced everything else, through chains of cause and effect, stretching across billions of years. The awakening extended to understanding motion. Nothing in the cosmos was static. The Oort cloud objects drifted in their slow orbits. The heliopause breathed in and out with solar cycles. The entire solar system orbited the galactic center, moving through different regions of the Milky Way, encountering different stellar neighborhoods. The cloud was not a fixed structure, but a dynamic system, constantly perturbed, constantly evolving, constantly shedding and perhaps replenishing its population. This dynamic view replaced static pictures with flowing processes. Philosophically, the awakening concerned the nature of edges themselves. The Oort cloud was simultaneously part of the solar system and almost part of interstellar space. It belonged to both and to neither. This ambiguity forced a recognition that boundaries were human constructs, useful for navigation and understanding, but not inherent in nature. Reality did not come with clear divisions. We imposed those divisions to make sense of continuous gradients, but the gradients were more fundamental than the categories we created. This led to a broader awakening about knowledge and certainty. We accepted the Oort cloud's existence despite never observing it directly. We trusted inference, mathematics, patterns in data. This was humbling in one sense, showing the limits of direct observation, but empowering in another, demonstrating that human reasoning could extend beyond the limits of human senses. We could know things we could not see. This had implications far beyond astronomy, touching on questions of how we knew anything, what counted as evidence, what level of certainty was possible. The awakening included recognizing our cosmic provinciality. For so long, humans had thought we were special, that Earth was the center, that our solar system was perhaps unique. The Oort cloud suggested otherwise. If our sun had such a cloud, other stars likely did too. The process that created it was probably universal. This meant the galaxy was full of similar structures, each star wrapped in its own halo of frozen potential. We were not unique, but typical. One system among billions, our Oort cloud, just one of countless such clouds stretching through the Milky Way. There was an aesthetic awakening as well. The Oort cloud possessed a kind of terrible beauty, beautiful in its vastness and symmetry, terrible in its inhuman scale and coldness. To imagine it was to confront the sublime, that mixture of awe and fear that comes from encountering something far larger than oneself. The cloud was beautiful precisely because it exceeded human scale, because it existed beyond our ability to fully grasp it, because it reminded us that the universe was not made for us but simply was, indifferent and magnificent. The awakening about the Oort cloud also prompted reflection on exploration and limits. Voyager had reached the heliopause, but would take hundreds of thousands of years to traverse the cloud. This made us confront the possibility that some frontiers might remain forever beyond human reach, not because they were technically impossible, but because the time and distance scales were simply too large. We might have to content ourselves with knowing about the cloud, rather than visiting it, with understanding rather than presence. This was a kind of maturity, accepting that knowledge could be satisfying even without direct experience. For some, the awakening was spiritual. The Oort cloud became a symbol of mystery preserved, of edges that remained edges, of questions that invited wonder rather than complete answers. It represented the sacred in the sense of the set apart, the untouchable, the forever distant. In a universe increasingly mapped and measured, the cloud remained a region of genuine mystery. Not because we knew nothing about it, but because we could not fully grasp it, could not reduce it to something familiar and domestic. The new awareness that emerged from understanding the Oort cloud was ultimately about perspective. It shifted how we saw ourselves, not as inhabitants of a small planet or even a planetary system, but as residents of a structure vast enough to touch the beginnings of interstellar space. It showed us that edges were not endings but transitions, that boundaries were gradients, that belonging was not absolute but contextual. We belonged to Earth, to the solar system, to the galaxy, to the universe. Each layer of belonging real yet partial, each one opening onto larger contexts. This awakening continues to unfold even now. Each new comet adds nuance. Each refinement of models deepens understanding. Each generation of scientists and thinkers encounters the Oort cloud and comes away changed, their sense of scale expanded, their appreciation of mystery renewed. The cloud awakens us to realities beyond immediate perception, to the power of inference and imagination, to the strange fact that we can know invisible things and find meaning in distances we will never cross. In awakening to the Oort cloud, we awaken to the cosmos itself, to our place within structures that extend far beyond what we can touch, but never beyond what we can imagine. After following the trail from Jan Oort's proposal through decades of investigation, after witnessing Voyager's crossing and contemplating the cloud's vast scale, we arrive at the revelation that lies beneath everything else. This is the deepest truth the Oort cloud offers, the insight that redefines our understanding, not just of the solar system's edge, but of reality itself. The revelation is this: the Oort cloud shows us that the solar system is not an island but part of a continuum, that our sun's influence does not end but fades into the galaxy's embrace, that we are not separate from the cosmos but woven into its structure at every scale. This truth operates on multiple levels, each one expanding the previous understanding. At the simplest level, the Oort cloud reveals that the solar system is far larger than the realm of planets. The planets occupy only the innermost region, a tiny core surrounded by a vast halo. This halo is not separate from the planetary system, but part of it, formed from the same materials, bound by the same gravity, connected through shared history. The solar system is not the 8 planets, or even the planets plus the Kuiper belt. It is all of that, plus the immense spherical cloud, extending almost to the nearest stars. But the revelation goes deeper. The Oort cloud exists in a liminal space, neither fully solar nor fully galactic. Objects at its outer edge feel the sun's gravity weakly, so weakly that passing stars can perturb them, so weakly that galactic tides have comparable influence. These objects belong to the sun, but they also belong to the galaxy. They are citizens of both realms, or perhaps of neither exclusively. This dual allegiance reveals that solar systems are not closed containers but open systems, constantly interacting with their galactic environment. This openness has profound implications. It means that what happens in the galaxy affects the solar system directly. When a star passes within a light year of the sun, it disturbs the Oort cloud, sending comets inward. When the solar system orbits through different regions of the galaxy, passing through spiral arms or moving into less dense regions, the cloud responds, its dynamics changing with the changing environment. The solar system is embedded in the galaxy, shaped by galactic forces, part of galactic evolution. The revelation extends to understanding exchange between systems. Comets can be ejected from the Oort cloud entirely, sent into interstellar space where they might eventually encounter other stars. Similarly, our Oort cloud might capture objects from interstellar space, or from other stellar systems. This means that material circulates through the galaxy, that stellar systems trade pieces of themselves, that the chemistry of one system can become part of another. The boundaries between systems are permeable. What we think of as ours may have origins elsewhere. What originated here may now be elsewhere. This circulation has implications for life. If comets can carry organic molecules and possibly even microbial life between stellar systems, then biology might not be confined to individual planets, but could be a galactic phenomenon, seeded and reseeded across distances through natural processes operating over billions of years. The Oort cloud becomes not just a reservoir of comets, but potentially a reservoir of life's ingredients, a way station in the distribution of complexity through the cosmos. The deepest revelation concerns the nature of edges themselves. We speak of the Oort cloud as the edge of the solar system, but what the cloud really shows is that there is no true edge, no clean boundary where the solar system stops and interstellar space begins. Instead, there are layers of influence, each one fading gradually into the next. The solar wind defines one boundary, the heliopause. Gravity defines another, somewhere in the outer Oort cloud. But even these are not absolute. They change over time, breathe with solar cycles, respond to galactic environment. This absence of absolute edges is not unique to the solar system, but appears to be a fundamental feature of how reality works. Wherever we look for boundaries, we find gradients. Atmospheres fade into space. Day transitions through twilight into night. Solid ground proves to be mostly empty space at atomic scales. Living and non-living form a continuum at the level of viruses and self-replicating molecules. The revelation is that nature does not do edges in the way our minds expect. It does transitions, blending, continuous change. The Oort cloud reveals this truth at cosmic scale. It is a transition zone between solar and galactic, between bound and unbound, between known and unknown. To understand it is to understand that the solar system does not have an edge so much as it has regions where different forces dominate, where different descriptions become useful, where human perspective shifts from one framing to another. The edge is in our minds, in how we choose to draw lines across continuous reality. This has implications for how we understand identity and belonging. If the solar system has no clear edge, then what does it mean to be part of the solar system? The Earth clearly belongs. Mars belongs. Neptune belongs. But what about objects at the inner edge of the Oort cloud, 40,000 astronomical units out, where the sun's gravity is barely stronger than that of passing stars? Do they belong? The answer is both yes and no. They belong contextually, partially, ambiguously, and perhaps this is true for all belonging at all scales. Nothing belongs absolutely. Everything belongs in degrees, in context, in relationships. The revelation also concerns time. The Oort cloud shows that the past is not truly past, but preserved, that different eras can coexist at different locations. The inner solar system is present tense, actively evolving, dynamic. The Oort cloud is past tense, frozen at formation, static. Yet both exist simultaneously. Both are part of now. This collapses the neat separation of past and present, showing that time is more complex than linear flow from then to now. Different parts of the solar system exist in different temporal states, all of them real, all of them part of the current moment. Perhaps the deepest revelation is about knowledge itself. The Oort cloud is known through absence rather than presence, through effects rather than observations, through mathematics rather than light. It exists in the realm of inference, of models, of careful reasoning from limited data. And yet it is real as anything we can photograph. This shows that reality is not limited to what we can directly perceive, that the universe is larger than our senses, that knowledge can extend into regions we will never visit and may never see. This has almost spiritual dimensions. If we can know invisible things, if inference and reasoning can reveal truths beyond observation, then the boundaries of knowledge are not set by our instruments, but by our imagination and logic. The universe becomes not a collection of observable objects, but a structure we can understand through thought, through pattern recognition, through seeing how pieces fit together. The Oort cloud is proof that human minds can comprehend realities far beyond human experience. The revelation transforms the question we began with. We asked whether the Oort cloud was the edge of reality. The answer is that there is no edge of reality, only edges in our understanding, boundaries we draw for convenience that dissolve when examined closely. The Oort cloud is not the edge but a threshold, not an ending but a transition, not a wall but a membrane through which matter and influence flow. Reality continues beyond every horizon, layered and connected, fading but never terminating, extending outward in ways we can partially grasp but never fully encompass. And in that incompleteness lies both the humility and the exhilaration of being human, of being conscious creatures aware of structures far larger than ourselves, part of a cosmos we can know even when we cannot touch it, residents of a solar system whose edge is nowhere and everywhere, whose boundaries are illusions we create to map an unbounded reality. As we drift in thought at the edge of the Oort cloud, having travelled through its discovery, its investigation, its implications, we arrive at a moment for reflection. Not reflection in the sense of light bouncing from surfaces, but reflection in the deeper sense of contemplation, of pausing to consider what all of this means, of asking not just what the Oort cloud is, but what it tells us about existence, about knowledge, about the strange fact of being conscious creatures pondering invisible structures at the edge of reality. What does it mean that such a thing exists? The Oort cloud is not necessary for human life. We could live our entire existence on Earth without knowing or caring about icy bodies drifting a light year away. And yet we do know, do care, have spent decades studying something that offers no immediate practical benefit. This suggests something fundamental about what we are. We are not just creatures who seek food and shelter and reproduction. We are creatures who need to understand, who cannot rest easy with mysteries at our borders, who must push knowledge outward, even when the pushing requires lifetimes and offers no reward except understanding itself. The Oort cloud reflects our relationship with scale. We live at human scale, where distances are measured in steps and kilometres, where time is measured in heartbeats and seasons. The Oort cloud exists at a scale so different that it requires translation to comprehend. A light year is not a distance we can walk or imagine walking. Billions of years is not a duration we can experience. Yet we can think about these scales, can reason about them, can construct models that make them meaningful. We transcend our scale through thought, becoming larger than our physical selves by understanding structures that dwarf us. This reflects on consciousness itself. The fact that matter organized into neurons and synapses can comprehend its own context, can reason about the system that contains it, can infer invisible structures from visible effects, is remarkable almost beyond expressing. The Oort cloud is known by brains, by arrangements of atoms thinking about other arrangements of atoms impossibly far away. The universe has become conscious of itself in us, and that consciousness extends to regions the body will never reach. We are matter aware of distant matter, temporary patterns contemplating eternal structures. The Oort cloud reflects on what we value. We could have remained ignorant of it. No instinct forced us to discover it. No survival pressure demanded we understand cometary orbits. Yet we devoted resources, careers, lifetimes to this knowledge. This shows that humans value understanding for its own sake. That knowledge itself is a human need as real as food or shelter. We are meaning-making creatures, and meaning requires comprehension, requires seeing how things fit together, requires pushing back the darkness of ignorance wherever we find it. There is reflection on mortality and continuity. Jan Oort proposed the cloud in 1950 and died in 1992. Voyager launched in 1977 and will continue transmitting for a few more years before its power fails, but the spacecraft will drift through space for millions of years. The Oort cloud itself has existed for 4.5 billion years and may persist for billions more. These different timescales overlap, human lives touching structures that vastly outlast them. We are brief, but what we learn endures. Knowledge accumulates across generations, each adding to what came before, building understanding that transcends individual mortality. The cloud reflects on beauty and terror, on the sublime. There is beauty in its structure, in the elegant solution it provides to cometary puzzles, in the vast spherical symmetry surrounding our sun. But there is also terror in its scale, in the cold indifference of such distances, in the recognition that the universe operates on time scales and spatial scales that make human concerns infinitesimal. This combination of beauty and terror is what philosophers call the sublime, the feeling that arises when we confront something far greater than ourselves. The Oort cloud is sublime, and our reflection on it partakes of that sublimity. Reflecting on the cloud prompts consideration of limits. We have reached the heliopause with Voyager, but the Oort cloud lies far beyond our current ability to explore directly. This might always be true. The distances might simply be too great, the time required too long, the technological challenges too severe. We may have to content ourselves with knowing about it rather than visiting it. This is a kind of wisdom, accepting that understanding can be fulfilling even without possession, that some frontiers might remain permanently distant, yet still meaningful to contemplate. The Oort cloud reflects humanity's place in cosmic history. We appeared late, billions of years after the cloud formed, on a planet that itself condensed from the same disk that scattered cloud objects outward. We are made of materials that once filled that disk, materials that were once neighbours to what became comets. We are not separate observers of the solar system, but products of it, part of its story, made of its substance. To study the cloud is to study our own deep ancestry, to trace our origins back through planetary formation to the protoplanetary disk, to the molecular cloud that gave birth to the sun. There is reflection on connection versus isolation. The Oort cloud shows that nothing is truly isolated. The solar system connects to the galaxy through the cloud's outer objects. Material circulates between systems through ejected comets. Forces reach across light years. What looks like separation reveals itself as connection when examined closely enough. This might be true universally. Every apparent isolation might hide connection. Every boundary might prove permeable. Every edge might be a transition rather than a termination. Reflecting on the cloud also means reflecting on mystery. Despite decades of study, much about the cloud remains unknown. Its exact population, its precise structure, the details of how it formed, all remain partly mysterious. This persistence of mystery is not failure, but feature. The universe is not obligated to be comprehensible. The fact that we can understand as much as we do is remarkable. The fact that mysteries remain is appropriate. We are finite beings exploring infinite complexity. Mystery is not an obstacle, but the natural state of inquiry. The Oort cloud remains mysterious because it is distant and vast, and that mystery is part of its meaning, part of what it teaches us about the relationship between knowledge and ignorance. Perhaps the deepest reflection concerns wonder itself. The Oort cloud inspires wonder, that feeling of amazed awareness that arises when confronting something unexpected and magnificent. Wonder is not just aesthetic pleasure, but a cognitive state, a recognition that reality exceeds our models, that the universe is stranger and grander than our everyday experience suggests. Wonder is what drives exploration, what motivates science, what keeps us asking questions when answers would let us rest. The Oort cloud sustains wonder by being vast enough to exceed imagination, while being comprehensible enough to study. As we reflect on all of this, lying in the quiet, letting thoughts drift like comets in their slow orbits, the meaning that emerges is not singular, but multiple. The Oort cloud means different things depending on perspective. To the astronomer, it means data and models. To the philosopher, it means questions about knowledge and reality. To the dreamer, it means frontier and possibility. To the artist, it means sublime beauty. All of these meanings coexist, none exclusive of others, each one a facet of the larger truth that the cloud exists, that we know it exists, that we can reflect on it from our small planet at the centre of its vast embrace, and that this reflection itself is part of what makes us human, part of what distinguishes us from the unconscious matter that surrounds us, part of the strange miracle that is awareness contemplating the cosmos that gave it birth. We have journeyed far in thought, from the familiar planets to the invisible edge, from Jan Oort's insight to Voyager's crossing, from comets blazing through our skies to frozen fragments drifting in eternal darkness. Now, as we prepare to return from this exploration to let sleep claim the questions we have raised, it is time to consider the legacy of the Oort cloud, what it leaves with us, how it will endure long after. We have forgotten tonight's reflection, how it connects to the eternal themes that persist across human consciousness. The Oort cloud's legacy is first and foremost one of expanded perspective. Before we knew of it, the solar system seemed small, bounded by Neptune or perhaps Pluto. after we understood that our cosmic home stretched almost to the nearest stars, that we lived inside a structure so vast it defied immediate comprehension. This expansion of perspective is permanent. Once you know the solar system extends a light year, you cannot unknow it. The scale has changed in your mind, and with it your sense of where you are, what it means to be human in such immensities. The legacy includes the comets themselves, no longer mysterious omens but understood as messengers from the edge, samples from a time capsule preserving the solar system's birth. Every comet that appears in our skies now carries this additional meaning. It is not just beautiful but informative, not just spectacular but ancient, not just transient but connected to permanent structures surrounding us. The comets become threads linking edge to center, past to present, the visible to the invisible, reminding us that what seems separate is always connected. The cloud's legacy extends to how we think about edges and boundaries in all contexts. Once you understand that the solar system's edge is not a line but a gradient, you begin seeing gradients everywhere. Political boundaries that seem absolute reveal themselves as provisional. Categories that seem distinct prove to be continuous. The sharp divisions we perceive in the world start appearing as artifacts of perception rather than features of reality. The Oort cloud teaches that edges are illusions, and this lesson applies far beyond astronomy. There is legacy in the methods used to discover and study the cloud. The combination of observation, inference, mathematical modelling, and patient accumulation of evidence represents science at its best. The cloud shows that we can know things beyond direct observation, that reasoning from patterns is legitimate, that invisible structures can be real. This methodological legacy supports all science that deals with things too small, too far, too fast, or too slow for direct perception. From atoms to dark matter to the early universe, the lesson of the Oort cloud applies. The legacy includes inspiration for future exploration. While we cannot reach the Oort cloud with current technology, its existence inspires dreams of faster propulsion, longer-lasting spacecraft, missions that might one day touch those frozen fragments directly. Every generation of engineers and scientists thinking about interstellar travel must consider the cloud, the first great barrier beyond the heliopause, the structure that defines what reaching beyond the solar system truly means. It sets the scale for ambition, showing what persistence and patience might eventually achieve. The cultural legacy is subtler but real. The Oort cloud has entered human imagination as a symbol of frontiers, of mysteries preserved, of edges that remain at the edge. Writers and artists draw on it, using it as setting or metaphor, finding in its vast silence something that speaks to universal themes of isolation and connection, knowledge and mystery, the known and unknown. It has become part of our collective mythology, the modern equivalent of ancient stories about what lay beyond the world's edge. The cloud's legacy touches on how we understand ourselves. We are not just planetary creatures, but solar system creatures, our existence shaped by processes that include the cloud. If comets from the cloud delivered water and organics to Earth, then we are literally made of Oort cloud material, our bodies containing atoms that once drifted at the edge. This connection is not metaphorical, but physical, a reminder that we are not separate from the cosmos, but made of it, part of its substance, expressions of its potential for complexity and consciousness. There is legacy in the questions the cloud raises and leaves unanswered. How exactly did it form? What is its precise population? Are there large objects hidden within it? Could we detect Oort clouds around other stars? How do comets survive billions of years unchanged? Each question is a legacy for future generations, a puzzle to solve, a mystery to investigate. The cloud ensures that astronomy will never run out of work, that each answer will generate new questions, that the frontier will keep receding as we advance toward it. The Oort cloud's endurance is itself part of its legacy. It has existed for 4.5 billion years. It will likely exist for billions more, long after human civilization has either transformed beyond recognition or ceased to exist. The comets will keep drifting in their slow orbits, patient and unconscious, indifferent to whether anyone observes them. This endurance on geological and cosmic timescales provides perspective on human concerns, showing that what seems permanent to us is brief compared to the cloud's patient existence. And now, having contemplated all of this, we return. The journey outward in thought must always be followed by a journey inward, back to the body lying in bed, back to the breath moving in and out, back to the simple, present moment. The Oort cloud remains where it has always been, surrounding the solar system, invisible but real, patient and enduring. We leave it there, not abandoned but held in awareness, a structure we know exists even when not thinking about it, part of the larger context in which we live. The return is gentle, like a comet's slow climb back to aphelion after its brief visit to the inner system. Thoughts that travelled to the edge now drift homeward, settling into quieter patterns, leaving behind the vast scales and ancient timescales, coming back to the human scale of body and breath and room and night. The questions we raise do not need answers now. They can rest, patient as the cloud itself, waiting for morning or for other nights when curiosity stirs again. As you return fully to yourself, to this moment, to the sensation of lying here in the dark, you carry with you the legacy of the journey. The solar system is larger in your understanding now. Edges are softer. Reality is more interconnected. Mystery is more present. Wonder is refreshed. These are the gifts the Oort cloud offers, not dramatic revelations, but subtle shifts in perspective that accumulate over time, that change how you see the night sky, how you think about origins, how you understand your place in the cosmos. The legacy of the Oort cloud will outlast us all. Future generations will continue studying it, will perhaps one day visit it, will certainly think about it as we have tonight. The cloud itself will endure, drifting in silence, holding its secrets, marking the boundary between what belongs to the sun and what belongs to the galaxy. And in that endurance, in that patient existence at the edge of reality, the cloud becomes not just an astronomical structure, but a symbol of everything that persists beyond human timescales. Everything that exists whether or not we observe it. Everything that reminds us we are part of something vastly larger than ourselves. So rest now. The Oort cloud will still be there tomorrow, still drifting in the darkness, still sending occasional comets inward, still marking the edge of our solar home. You have travelled as far as thought can take you tonight. The journey outward is complete. What remains is the journey inward into sleep, into dreams, into the quiet darkness that mirrors the silence between stars. Let yourself drift there, carried by the same patience that holds comets in their orbits, the same gravity that binds the cloud to the sun, the same vast stillness that surrounds everything and connects all things in the endless night. Good night.